Alright, so starting over here again because I don't like my last video. I wasn't thinking very clearly. I'm kind of tired tonight, so bear with me. So this lecture this morning went over 6 different things, and I kind of liked it because he kept it pretty coherent with those 6 different things and how each subject led to 6 of these pathologies that we talked about, covered this morning. So the first thing we talked about was edema. So edema is caused by outpouring of protein pore fluid into the tissues. So it can be caused by a lot of different mechanisms, or there's a lot of different pathological mechanisms behind it. So we've got I've got 5 of them listed here that he went over in specifics and gave examples for. So the first being hydrostatic pressure, or an increase in it. So hydrostatic pressure is basically your blood pressure. The more pressure you put on a vessel, or the fluid in the vessel, the more pressure you put it under, the harder the vessel, or the harder the fluid is going to push out against the walls of the vessel. And that can cause it to seep through. The more pressure that's on it is going to push more fluid into the tissues through the capillary wall. All right, so increase in hydrostatic pressure will do that, or will cause edema. You can also have a decrease in colloid onotic pressure to cause edema. So colloid onotic pressure is the other big mechanism, and let me think of a good way to explain this. Colloid onotic is the osmosis gradient, or the concentration gradient of water in a tissue. So normally we have a specific amount of albumin, which is the major protein in our blood, as we learned, and it's tightly regulated within our bloodstream. If we get a decrease in that protein, that's going to cause fluid to escape outside of the capillaries, because we're not going to have a bunch of solute in there like we normally would. So a solute, we all know that water, according to osmosis, moves to balance out solutes. So the more of sodium or albumin you have in a compartment, and if you put a membrane between them, in this case the capillary, it's going to move to wherever the most solute is. So the most sodium, the most albumin, whatever you have, it's going to move to kind of dilute that concentration difference. So if we decrease the amount of albumin in our blood, we're not going to have as much protein there, and there's going to be much more within the tissues outside of the capillary, so the water is going to move to balance out that difference in concentration gradient. So another big pathological mechanism. Our third one is our sodium retention. So anytime you retain sodium, which can be caused by the renin-angiotensin-aldosterone system, or kidney injury or stuff like that, you're going to increase the amount of water you also retain because of that. So if you get a lot of sodium retained within your system, you're going to have a water overload, and you can manifest that in a lot of different ways. You could manifest it in systemic edema, but the most important place you're going to manifest it is in your legs. So this is a good example of your pitting edema. So pitting edema is caused by heart failure, usually, congestive heart failure. And when you push down on somebody's leg, you're going to make an indent from your thumbprint or your fingerprint, whichever you have. And it's caused by, for one reason, an increase in sodium retention, because your heart is not pushing as much blood through your kidneys to filter out that sodium. Okay. Number 4 is going to be your lymphatic block. So this one I always enjoy because of elephantitis. So elephantitis is a condition where the lymph channels in one region of the body become blocked. So we all know that the lymphatic vessels, they carry away your fluid that is not blood back to the ducts to be put back into your bloodstream. And when those get blocked, the fluid that is within the tissues has nowhere left to go. So it just accumulates there, and it accumulates and accumulates and accumulates to the point where you have vast swelling of this protein poor fluid. And it can manifest itself in a lot of different spots in the body, but you can get an arm with the lymphatic vessels blocked that can expand to like 10 times its size. And that's why they call it elephantitis, because you look like you have an elephant's appendage because it's so big because of that block. It can also be blocked by a tumor, I should mention that. And then you have inflammation. So inflammation, the mechanism behind it is that, well, we covered that in microbiology, but when you have inflammation, you're basically going to have vasodilation, and the epithelial cells of the capillary are going to constrict and allow the protein and fluid to move through the spaces between them into the tissue. So when you have inflammation, it allows all that protein-rich fluid that would normally stay in the blood to sneak past the epithelial cells out into the tissue where your vessel is located. So a good example of this would be a pleural effusion when you it's caused by an infectious agent, and you have an infection in your pleura or in the lungs or in your viscera, parietal viscera. That's going to cause a huge inflammation response by your body, and your epithelial cells contract in your capillaries in your either parietal or visceral pleura, and then that's going to allow the fluid to sneak in, and it's going to accumulate in the pleural space and cause a pleural effusion. All right, so the second thing he talked about was hyperemia and congestion. And I know I'm not going over all the different examples that he listed in class of edema, so I don't think I'll have time for that in one video. So I'll just let you go through and look for the mechanisms, examples of each mechanism, because he lists one for each at least. So hyperemia and congestion. Hyperemia is just like an increase in perfusion of tissues. So an increase in perfusion of tissues, the good example, he didn't really go over this too much, which is kind of good because you can't really, there's not really many clinical examples of it. But the clinical example he gave of hyperemia was blushing. I can think of another one is of the niacin flush that some people can get from drinking like energy drinks or pre-workout or something like that. Let me look here. Yep, and then he also said conjunctivitis can cause hyperemia, so that's like bloodshot eyes. Basically, this just means you're increasing the blood flow to a specific tissue. When you get, like I said, when you drink an energy drink, a lot of times they overload that stuff with niacin, which is a vitamin, and niacin, for some reason, I don't remember why it does this, but it makes the tissue in your face become hyperperfused. An example of hyperemia, just like you're blushing, except it's not actually you blushing, it's because of the amount of niacin they put in it. And that's supposed to make you feel like you're waking up or something like that, but it's just a trick that they do to make you feel like you're getting your money's worth. All right. And then congestion would be the exact opposite. So congestion would be long-term poor oxygenation of a tissue, or hypoperfusion of a tissue. So the example he gave was liver congestion. So they call that chronic hepatic congestion. And he didn't really mention anything onto the mechanism or why it happens. But just know that eventually the cell's going to die. The cells of the liver would die if they're kind of exposed to a congestive process. All right, so our third thing we went over, and a lot of people have been asking me about today, is hemorrhage. So hemorrhage, he goes over a lot of different stuff in it, But the main thing he goes over is our clotting cascade and how that works in the lab. So he didn't actually touch on the in vivo model of coagulation. And I actually kind of like that because it keeps it, I have a really good simple way of remembering our in situ or in lab methods of clotting. So we've got kind of two clotting cascades that converge onto a common cascade with our coagulation models. So we've got our intrinsic and our extrinsic pathways. So intrinsic is going to be caused when we have an intrinsic injury to like our endothelium. Okay, so one example of this would be the shear stresses on your vessels. Since if you have high blood pressure, your vessels are going to undergo a lot of shear stress, and they could have little nicks or cuts in them. And that's going to expose our factors that are necessary to activate this clotting cascade. So the way to remember this arm of the clotting cascade is with the acronym TENANT. So we're all tenants in an apartment or something like that, at least most of us are. And the TENANT acronym serves to give you the first letter of each of the factors necessary. So T stands for 12, and when we get insult or injury from the intrinsic pathway, that's going to allow the 12 to turn into 12A. So anytime I say something is activated, it just means it's got an A behind it, and when something's activated, it's going to be able to turn and activate something else. So when we get 12A, we're going to come to 11, and this is going to be used as an enzyme to convert 11 into 11A. And 11A is going to be used as an enzyme to turn 9 into 9A, okay? And then 9A is going to be used as an enzyme to turn 8 into 8A. And then 8A is going to be able to turn 10 into 10A, okay? So it's just a big, long, kind of convoluted cascade that allows us to form a clot. But there's specific reasons why we have each of these arms, and that's what I really hope to explain. It's that when we have this pathway, the intrinsic pathway, there's certain drugs that act upon it, namely heparin. And if we measure only this pathway by providing some type of intrinsic signal, in this case, like in the lab, like glass beads or a negatively charged ion, we can measure heparin's effect on the time it takes to clot a sample of blood. So why would that be useful? Well, it'd be useful if we were trying to figure out if we've got the right amount of heparin in the person's system so that their bleeding is not super coagulable, so they're not forming thrombuses all over, or they're at a sufficient, or they're not too high on the scale of heparin dosage that they just be bleeding out no matter what. Okay. So the test that tests this intrinsic pathway to clot formation is called the activated activated partial prothrombin time. Excuse me. Activated partial prothrombin time. I think this is actually the or APPT. All right? And that is directly influenced by heparin. So what does heparin do? Heparin, quizzically enough, actually inactivates or causes factor 10 to not be able to form a complex with 5. So I should have explained the common pathway first, but I'll do that now quick. So when we get to the final end of this intrinsic pathway, and also the extrinsic pathway, as we'll see, we get to this area called the common pathway. And both intrinsic and extrinsic pathways share this way that they make the final clot. So the 10A, when it's activated by 8A, it complexes with this other factor in calcium and phospholipids, which you don't need to know as much. But it's going to make this big enzyme, when it assembles with this, to allow prothrombin to turn into thrombin. Okay? So those two together make an enzyme that turns prothrombin into thrombin, and thrombin is the enzyme that turns fibrinogen into fibrin. Easy enough, right? Well, heparin is going to come along and it's going to block factor 10. So you can't, or you can no longer get any of this. It's also going to act upon this molecule called antithrombin. So antithrombin is a way of your body controlling the amount of thrombosis made within your system. And heparin is going to bind to this molecule of antithrombin, which is actually one of the only thing I think that makes sense named in the coagulation cascade like it is, because we know that, or the name literally implies it's going to do the opposite of thrombin. It's going to come in when it's bound to heparin, and it's going to be able to cleave thrombin, which I forgot the M here, back into its original form of prothrombin. So it's going to cleave into two different molecules. And that's going to cause us to break down some of our clots. So two ways that heparin works: it's going to block factor 10, it's going to actually break down thrombin through antithrombin. How does it do that? Heparin just binds to this molecule and allows it to actually break thrombin down. All right. Now we've got our intrinsic pathway, or our extrinsic pathway. This is the basis for the prothrombin time test. So in this method, we've got an extrinsic insult. So this is like a tissue factor, or when we get, like, say somebody stabs somebody or something like that, God forbid, I don't want that to happen, but say it did. And the injury would cause a factor to be released from the tissues that are open in the cut. That's why it's called extrinsic. And that would go ahead and activate this factor 7 to be turned into factor 7A. So this is a much simpler arm of the clotting cascade. And factor 7A is going to do the exact thing that 8A did in our intrinsic pathway. So it's going to allow factor 10 to turn into factor 10A. And then that's going to complex with factor 5, turn prothrombin into thrombin, and fibrinogen into fibrin. Now, why do we need a pathway to measure this? Well, warfarin, the drug found in Coumadin, which is actually a rat poison, fun fact, really affects this specific complex, or this factor, really well. So warfarin is a drug that blocks vitamin K, or decreases the amount of vitamin K that we have in our system. And these factors, or this factor specifically, and a couple other ones, are made in the liver. And if we have a sufficient amount of warfarin circulating in our system, it's going to block vitamin K. And vitamin K is needed to make this factor in the liver. So if we can't get factor 7 circulating within the blood, because it's not made in the liver because warfarin is blocking vitamin K, then they're going to go ahead and lengthen the time that it's going to take to form a clot, because we're going to need to find enough factor 7 to be able to activate into 7A and thus make our common pathway work. So that's the easiest way to remember the prothrombin time. It's going to test for warfarin. And what does warfarin do? Vitamin K. An easy way to remember that is if we need a reversal agent for somebody who's having a stroke, which is super common in the ED where I did my time. If they were on warfarin and they were having a hemorrhagic stroke, which is where you get diffuse bleeding in the brain from a burst vessel, we gave him vitamin K, because if